Hello, 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 hello. Hello, 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 hello. I hope I'm audible. Let's start in 1 minute. Yeah. So, hi everyone. This is Devansh here, and today we are going to discuss the beautiful problems of Leetcode Contest 492, which was a weekly contest. So, yeah. So, let's start. So, there were total 4 problems on today's contest, and we are going to discuss all of them. So, first of all, do ping out how many questions did you solve today if you gave the contest, because it was in the morning. And in the morning, we feel lazy. But yeah, do ping out how many questions did you solve in this contest. And today we are going to discuss all the 4 problems. So yeah, this one was pretty easy and straightforward. I think this was also pretty straightforward. This required some observation, the third question. And fourth question also required some observation. Not that much hard or like that much complex too. But yeah. So yeah, let's start one by one. First, we'll read the problem and then we'll understand it using an example. Then we'll move out towards the observation and intuitions we could make up using the problem statement as well as the example. And then finally, we'll move towards the solution. So this would be our framework for approaching each of the 4 problems. And then we'll discuss the code and my code and my solution. And then we may move forward. And if during any question you think like you have a better approach, you can always ping it out in the comments. I will be actively watching comments even after the stream. So it wouldn't matter if you think you have some doubts or if you think you have a better approach for any problem, you can just ping it out in the comments. So hope that sets. Let's start with the very first problem. So minimum capacity box. You are given an integer array capacity where capacity I represents the capacity of ith box and an integer item size representing the size of an item. Okay, let's start. So this is the problem A, right? First thing we are given a array capacity. This tells us capacity. As the name suggests, it tells us about the capacity of the uh, array or capacity of the box, right? Of the ith box. Great, got it. So this is an array. Got it. Second thing we are given is item size. We have one item and we are given its size by item size. Okay, got it. I hope this part is clear. The ith box can store the item if capacity I is greater than equal to item size. Yeah, that's also fine. When would a box will be able to store this item? When its capacity is greater than or equal to, when its capacity is greater than equal to item size. Yeah, sure. The ith box will be able to store the item when its capacity is greater than or equal to ith to the item size. Got it. Got it. Okay, got it. So what we need here, we need to return an integer denoting the index of box with minimum capacity that stores the item. If multiple such boxes exist, return the smallest index. If no box can store them, store the item, return -1. Okay, got it. So what we need to return here? What do we need? We need smallest and least index of a box which can hold the item. Yeah, great. This is our question. This is our entire question. Okay, great. So how are we going to solve it? First, let's also understand it deeply using an example. Let's take this example. So we are given these are the capacities, right? This is our box. Each index here tells us about the capacity of ith box, how much that box could store. And we are given item size as 3, right? Yeah. So basically now we have to find the smallest box which could hold it. Can this box hold it? No, it cannot, because this is less than 3. Can this box hold it? Yeah, this can hold it. Can this box hold it? Yeah, this can hold it. Can this box hold it? Yeah, this can hold it. Right. We got 3 boxes that could hold it. Now we out of them, this is the first criteria, that the capacity should be greater than item size, greater than equal to. The second criteria is we need the smallest box. Right. Which is the smallest among them? This one. Right. So we are going to return this index, which is 0. This is the 0th index. This is 1. This is second. This is third. So we are going to return 2. Right. Now let's just take one more example. Let's say we had an the capacity like this. Right. And again our item size is equal to 3. Now, can this box hold the item? No. Can this box hold the item? Yes. Can this box hold the item? Yes. Can this box hold the item? Yes. So this was our first method to decide which boxes can hold. Second, we need to know the smallest one. The smallest one are with the least capacity. This is the smallest one, and this is also the smallest one because we have two boxes, two identical boxes. Now, if we have identical boxes, we have to return smallest index. Index. The index of this is 1. Index of this is 1, which is smaller this one, right? So this would be our answer. So this entire example actually demonstrates the answer to. So we just have to take these 3 criteria and we just have to implement them. And how are we going to implement them? Implement it. Hello, hello. Let me just check. Okay, got it. Yeah. So to implement it, yeah. So we just have to take these 3 criteria and one by one we have to iterate among them and see if answer exists or not. Or there could be also one more this case. Let's say we have this. These are our capacity of our boxes and item size is equal to, let's say, 7. Now neither of these boxes can hold it, then we are going to return -1. Right. So what could be our answer? Let's let's take this example. What could be our answer? How are we going to calculate it? It's just an implementation problem where we need to decide all these 3. So what we could do is, now algorithm, we are going to iterate left to right and see who fulfills our criteria. Fulfills criteria. And how does this work? For each element, let's say we are iterating from left to right, we are going to see if the current box we have, the current box we have, if this current box is greater than the capacity I, this current box is the current box we are storing it. We are iterating from left to right, right? And we are also going to check one more condition. If capacity is greater than equal to the item size. If we go left to right using this algorithm, this would always work, right? Because if we are going left to right, we are always taking the best possible box. Let's say we have 7, item size is equal to 3, right? And we have 7, 3, 4, 5, 4 and 1. So we will go here. Current box is equal to, let's assume this is infinity, 1e9, right? So this is current box is 9. Is this less than our current box? We need, is this less capacity? 1e9? Yeah, this is. Also, is this greater than equal to item size 3? Yeah, this is. We check, we checked both conditions, and then our current box, in this current box, will store 7 because now we are storing it in this box. Similarly, we will go here and we'll check if 3 is if 3 is less than, if this is less than 7. This is our current box right now. And is this greater than equal to 3? Both again will be true and our current box would update to 3. Now for this condition would fail because this is not less than 3, right? And although this is greater than equal to 3, this condition follows, but this doesn't. So it would not take this. And for this too, this condition would fail while this condition would pass, right? So our final answer would be this, the box, the first box. And we are also going to store current box index. Every time we take it, both the conditions are satisfied, we also take. Initially it would be -1, but later when we take 7, it would become 0. And when we take this element 3, this would become 1. So in this case, we take the first element which has which is the smallest element with the capacity to take item size. So this is the algorithm behind it. Let's also go through my let's once also go through my solution that I wrote during the contest. Yeah. So again, this is our current box and this is our index. This is our condition that we are checking. First, we check if the current capacity is less than the box we are holding it. And second, we check if that capacity can hold the item or not. If it's capable, then we are storing it and then we are finally returning the answer. So yeah, this was actually pretty straightforward implementation problem. Typical Leetcode weekly or bi-weekly first question. I hope it is pretty clear. If you have any doubts, you can actually ping it out in the comment section. Okay. Now let's move towards our second question. Let's start from here. Yeah. Let me also check the comments. Did you solve all the problems while contest? Yes, I did, dude. Yes, I did. Do ping out how many questions you also did in the comments. Okay. Let's start with the second question now. Find the smallest balanced index. You are given an integer array nums. Okay. The an index I is balanced if the sum of elements strictly to the left of I equals to the product of elements strictly to the right of I. Okay. Let's start with the second question. The problem B. Here, first thing we are told are we are given an integer array nums. Right. Second, we are given we need to find a balance. We are given definition of balance index. A balance index is an index, let's say this element is a balance, such that the sum of all the elements strictly towards the left, their sum, and product of all the elements strictly towards the right, its product are equal. These two are equal. This is what we are told. Right. And what we need to find is if there are no elements to the left, the sum is 0. If similarly, if there are no elements to right, the product is 1. Okay, got it. That means if there are no elements, sum equal to 0. And here no elements, the product would equal to 1. Prod stands for product. Okay, this would be equal to 1. Got it. And what we need to find, return an integer denoting the smallest balance index. If no balance index exists, return -1. Got it. What's our problem? We need to return smallest balance index. Balanced index. If there is no such index, no index is balanced, we are going to return -1. Right? Pretty straightforward problem. It tells what to do. Got it. So let's move forward. This is the entire problem. Let's take some example to understand it. 2, 1, 2. Got it. 2, 1, and 2. Right. Let's check for each index if it's balanced or not. For this index, as there are no elements, sum would be equal to 0. Right. For this problem, we are going to denote sum by S and product by P. Right. For just for notation. Right. Just to make things easier. So here sum would be equal to 0 and product would be equal to 2. Right. And sum is not equal to product. Right. For this index, so this could not be the R index. Got it. Now again, let's check for some other index. Let's check for, now again 2, 1, 2. Let's check for this index. The sum would be equal to 2 and the product of all the elements to its right would be equal to 2. You know na, the product, how we found the product. The product was all the elements towards its right. All the elements towards this is right is 1 and 2. So this would be 1 into 2 and that gave us 2. And the sum would be all the elements to the left. Initially there are no elements, so it's already given that if there are no elements, take the sum as 0. My bad. Yeah. So similarly, we have our product equal to 2. Are they both equal? Yeah, they both are equal. That means this is our index. Should we check all other elements too? Should we check all the elements too? No, right? Because we need the smallest possible index, right? This gave us our first observation too, right? We'll start from left. We can start from left. Okay, great. Also, there is one more thing that we have to notice, right? The product would always increase and the sum would always the sum would always increase and the product would always decrease, right? So can we say that there is only one index? Can we say this? Why? Because the sum would always increase, right? As we move on the right side, the sum would always increase. Let's say we start iterating from left to right, sum would always increase and the product would always decrease. So if there is some equilibrium where sum is equal to product, later what will happen when we go right, that this would increase and this would decrease forever. That means that there would be only be one index. There could only be one index that satisfies the problem. That satisfies, right? So this tells us that there exists only one index that is balanced. Great. One more important thing here are the constraints of the problem. We are given that for each index for each element, where should I place? Let's do it here. This is also part of problem, right? For each element, this is less than equal to 1e9 and n is less than equal to 1e5. Right. So these are our observations, right? We could just what we could do here. How are we going to implement it? This is also straightforward problem. This is just an implementation problem. How are we going to find? We could actually start from the leftmost index. Let's actually discuss here. Let's take an example 212. We can start from this index. We can somehow store the all the products here. And as we move forward, we could actually divide this number by product or that element by product, right? Can we do this? Yeah, we can do this, right? We can actually store some product initial. This is product of all numbers, and we can apply it. But there is one problem with storing the product of all numbers, right? Uh, what my intuition was for this, let's take we have number 2, 3, 5. Product of all numbers would be 2 into 3 into 5, which is 2 into 3 is 6, 6 into 5 is 30. So this is product of all numbers, right? And what we could do is we could iterate from here. We could keep a sum variable which is initially 0. And for this too, as we reached here, what we'll do is 30 divided by 2. So this would become 15. And we'll check if sum is equal to product or not. This is not, right? And then we'll move towards this. And while we move towards this, we are going to add sum plus equal to 2. We are going to add 2 to our sum, right? So our sum would be equal to 2. And now as we reached here, we are going to do product divided by 3, which is 15 divided by 3, which gave us 5, right? Are they equal? They are not. And for this, again, what we are going to do, first we are going to add sum 2 plus 3, because 3 is the new element we have added. So this would be equal to 5, and product would be equal to 5 divided by 5. This would be equal to 1, right? Are they equal? They are not. So we are going to return -1. But the problem here is, the problem with is calculating all the product. We know each nums is 1e9, right? At max, it's 1e9. I am assuming you all know what 1e9 means. 1e9 means 10 raised to power 9, right? So we know each nums I, each element is less than equal to 1e9, right? So let's assume if all the elements are 1e9 and we multiply all of them, wouldn't be our product be equal to 1e9 into 10 raised to power 5, or n, which is equal to 1e5? This is too large, right? We cannot store this in long, right? We cannot store this. So how are we going to solve this problem? We just made one observation here. There is only one index, right? We were starting from the leftmost index because we required the smallest index. But we came to know there is only one index. So can't we start from the right? Start from right. If we start from the rightmost index, now let's change the tables. Now we would require the sum, total sum, right? For this equation itself, let's say this. Let's take this. Got it. Now for this, what would be the sum? Sum would be equal to 2 plus 3 plus 3 plus 6. This would be equal to 6 plus 3 is 9. 9 plus 5 is equal to 14. Now, now, we could start from the right. Initially, our product would be equal to 1. And at each index, what we will do will two steps. First, we'll multiply product with we are going to multiply product with the nums I, with that element, or nums I, or whatever ith index that we are going to start. And then we are also going to subtract its sum minus this element. and then we are going to check, right? So this is our algorithm. We'll start from last. This is the first step. Start from the right. This is the second step we are going to implement at each index. Let's say we implemented here. Our sum would go 14 minus 6. This would go 8, and our product is going to go. Initially, it would not go. This step we'll do after checking. After checking. Right. Initially, our product would be equal to 1. Are they equal? S is not equal to P. And then what we are going to do, we are going to update P by initially it's 1 and 2. Now this element 6. Then we will go here and first we'll subtract the sum. Sum would be equal to initially it's 8, right? 8 minus 3. This would become 5, right? And then we'll check our product. Product would be equal to 6. Are they equal? No. In this example, they are not equal. But let's take, let's say we had this example 2, 3, 3, and 5. Now, our total sum is equal to 13, right? It is sum of all elements, and product is equal to initially 1. For this example, what is our first step? We add our sum. We subtract our sum. 13 minus 5 is equal to 8. Second is we check. Here S is not equal to Py because 8 is not equal to 1. And third is we multiply, which is what we do? We do P equal to 1 into 5, which is equal to 5. Similarly, for this element, let's say we did. Now sum would be equal to 8 minus 3. So this would be equal to 5. Now, is sum equal to P? Yes, because this is also 5 and this is also 5. So we are going to return this index, which is 0, 1, 2. So we are going to return second index. So this algorithm we basically iterate from last to first, and where we do this for each element. Just make sure there's one more thing that you need to notice. While calculating product, this doesn't exceed long max or whatever. You can actually ideally, to make sure it doesn't exceed the long limit, or 2 to the power 64th limit, the long l- the limit for the long, to make sure it doesn't exceed the limit, it should not be equal to this, right? To make sure, you could actually add some if conditions. First, you can actually always break when product is greater than sum, right? Because when we are moving from last to first, we know that the product would always increase and sum would always decrease. If product is already greater, it would only increase if we move further, right? So we can break, and we can also check if product ever becomes greater than long. How are we going to check it? I'll show it in my code. We can actually break. So this was an entire algorithm that I used, right? Step by step, and then this is how we derive the answer. Let's actually see my code. So, yeah. So this is my code. Just 1 second. Yeah, this one. First, this is our total sum. I'm using accumulate function. If you are not aware of, this is basically just calculating the sum of all the elements in the array nums, right? You can use it if you are using C++. And then this PD tells us about our product, which is initially equal to 1. At each step, we have already defined our steps. First, we decrease our total sum. Then we check if it's equal to 0. If they are equal, we just return the index, because there is only going to be one index. So we don't need the smallest index. And then if these are the break conditions, if product is greater than sum, we break it. If product is, now this is basically used to just see this condition. Product should be, if product is greater than long. What this means is, before multiplying this element nums I, what I do, I need to check if multiplying this would exceed our current integer limits, right? That means this is greater than long or not, right? Instead of checking this, what I could do is I could basically divide it here, because this is going to overflow anyways, right? So basically I did this. Yeah, just to see the overflow, right? Because during contest I was just thinking I just need to pass it. Didn't waste that much time here. Yeah, so this is how we check the overflow, and this is what we are doing. Our third step, which is basically multiplying the product. Yeah, so this was about the third question. Hope you get it. The time complexity for this would be O of n is O of n, right? Because we are just iterating the array, and the space complexity would be O of 1. I don't think we are storing it, right? We are not storing anything. We're just storing few constants, which are few variables. We are not storing anything else. So this would be our time complexity as well as space complexity. Hope you guys love like the solution. If you guys think you have better approach or some an other approach or some other observation you did, can always ping it out in the comments, right? If you had any doubts, you can also have any doubts, you can also ping it out in the comments. Let me, before moving towards our third question, let me actually see the comment section first. You solved three problems, cool dude. You also solved three, cool dude. You solved two. We are going to discuss third problem now. You can actually see it. Start from the last index, stop the product exceeds total sum. Yeah, that's it. That's also great. This is what we did. Solve three, but the rank is low than previous. I don't know. For the past contest, I felt that getting your rank is much harder. From the past contest, I believe it's pretty easy to solve all the four questions. So yeah, like past few contests, there are less of logical problems. And also it also depends on how, like if you did three questions, how early did you did or how fast did you did. It matters a lot for the rank. Really matters a lot, and how many wrong submissions you did, because that also increases the time penalty, right? So that might be the reason you are not getting that much positive delta. But yeah, solve fast maybe could help. Now let's actually discuss the third problem, which is minimum operations to sort a string. Okay, great. You are given a string S consists of lowercase English letters. In one operation, you can select any substring S that is not the entire string and sort it in the ascending alphabetical order. Okay, so we are given, so this is our third question. First, we are given that we are given a string S, right? And we are given this operation, what we could do, and we could sort a substring. What does this mean? Let's say we add this substring. We can, if we are uh, going to, let's say, sort, we can sort a substring. If you are going to sort this substring, this answer would be A, B, C, and D, right? In one operation. Okay, return the minimum number of operations required to make S sorted in ascending order. If it's not possible, return -1. Third, which is what we need to find, minimum operations sort the string. Sorting means just basically ordering the strings from lowest to the highest. To sort the string, if we can't, answer in -1. Answer -1 or return -1. Otherwise, we'll return an integer, right? Positive integer. The number of steps we take. Okay, great. Let's understand this using an example. Yeah. Let's say we had this dog, dog, O G. Sorted. What would be a sorted string? Sorted string would be D, G, and O, right? Right. This is the sorted string. This is our answer that we need. How many steps? How many minimum steps we need? You can. It is pretty straightforward for this problem. If you take this substring and sort this, as this is substring, this is a valid operation. We could actually sort it and make it DGO, which is our answer. So this happened in one operation. So we'll return one. Okay, great. Let's also see one more example. GF. Okay, GF. Yeah. So our intended string is FG. Why? Because F is less than G, because F comes earlier in the alphabets, right? Comes earlier. Right. So this is a F is less than G. So this is a intended string that we need. How many operations can we do? We can actually make an operation to entire string, but that would be invalid. We can only do operation on a substring. We can only do operation on a substring, so this would be invalid. So can we do something to sort it? No, there is no way, right? We can only sort this is a substring, but there would be no point in sorting it, right? We need to swap both the characters, right? And we cannot do it by any operation. So yeah, we cannot do it, so we are going to return minus, right? So how are we going to solve the problem? Let's actually, there are few things that we need to notice first. For any problem, observations, whenever this problem occurs, when we are required to ask minimum operations or maximum operations, this is just one trick, you can say. You can always think, can we solve it using fixed number of operations? That might be 0, 1, 2, or can we solve it using this operations or this, right? This actually helps a lot in majority of problems, right? Whenever there is an operation using some minimum operation, always think what could be, can I solve it using only a subset or only a selected integers or not, right? Again, back to problem. So one of the observation here is to sort it, what we needed is we need this smallest element on the first index. Can I say this? Smallest here. And we need the largest here. This is our first observation. Can I say this? For any string, we need the smallest element here and the largest element here, right? So also there is one more thing that we need to notice. For let's example, we have this DGO. It's already sorted. If it's already sorted, how many operations we need? We need 0 operations. So this is our second observation. If it's already sorted, we need 0 operation, right? Because this is already sorted. This is our answer. This is our question as well. So we will need 0 operations to solve this. Okay, great. So this was our first observation, that the smallest element should always be the first and the largest element should always be at the last index. Got it. Now, building on to this observation, for any string, let's say D, C, M, N, X, Y. Let's take this example. Just just as I told, let's assume we could solve it whenever this operation occurs. What I thought was, can I solve it using this number of operations, 0, 1, 2, or something like that, the least integers or not? We already know if the element is sorted, we will return 0, right? And if we cannot sort it, right? We are going to return -1, right? Now we are going to think when are we going to sort how can we sort the element? We know that we need the least element here and the maximum element here. For this string, we know the maximum element is already here. This is the max. But the minimum element, which is the minimum element or minimum character here, this is here. So can I do this? What if let's think, what if I started I take this substring once, right? And I take this substring once. What is the probability the string would always be sorted? Right, what is the probability? Because let's say we took all this, we took the maximum possible string we could, right? And what would this would do is this would basically place this operation. Let's assume in first operation what we do is we place smallest element. What would be the best possible to sort this? If our operation allows us to sort entire string, this would always take one operation, right? Right, let's build into this. For any string, for any string, if we could sort entire, right? If we could sort entire substring, entire string, this would take us always one operation or maybe zero if the string is always sorted, right? What if I did if I also know one thing is like the first element would always be smallest and the largest element would at the last. If the smallest element is on the beginning, is at its position, I could just use this to basically I could actually place it here and then apply the sorting on the rest of the string, right? We place the smallest or largest, and then second what we do, we sort the rest. Why do we need to do it? We cannot. Why do we need to do it? We can't sort entire string. We cannot sort the entire string, right? So what we could do is if we place the smallest element at its position or the largest at its position, we could just sort the rest of the array. For this example, let's say we have this. This is our algo, right? So let's say this example DECOXMN. We need to sort it. Let's place the first element at its position. To place first element at its position, I had to take the prefix that includes the first element. This is our first element, right? We need to take the prefix that takes the first element. That takes the first element. If we take this prefix and we sort it, our string would be C, D, E, and this would be as it is. OXMN. Right. Now. This position, this is at its correct position. Right. Now I can just sort the entire array. Right. This is a star observation. If I anyhow am able to place the first position as the least element or the last position as the least element, I could basically do one operation for this, and I can do second operation. I could just sort the rest of the array, right? This would take me only two operations, and this would be the perfect answer, right? If there could be possibility, for example, for this question, DECX, this is the largest element and this is already at the last. That means first, our first condition is already satisfied. For we just need to basically sort the rest, right? So this would take one operation. So for this, our answer would be one, right? So this tells us if first and last is already satisfied, first or last, right? Or are already good. That means it will take us one operation, but because we would just need to require to sort the rest of the array, right? So this is our condition that we need to know. This is our algorithm. But there is one edge case with it. There is one edge case with it. What if our first element, let's say this is the array A, B, C, F, H, right? Now our largest element is there and smallest element is there. Let's apply our first operation. First operation was to basically sort the prefix with element at sort the prefix with first element, right? If we are placing the first element, so yeah, we basically sort this, but this creates a problem. This takes the entire array, right? Similarly, if we sort to for last element to make last element at its position, we have an option here, right? At the first condition, we could place the smallest element or the largest element to its position, right? So if we did this, if we sort the largest element, we would require the suffix that includes it. The suffix that includes this is also an entire array. So again, we cannot take it, right? So if this condition occur, what I could do is, what if I just sorted this portion? If I sorted this portion, this would return in F, C, A, B. Now our element is ready to basically, now I can take this prefix, right? This would take us one operation. And now when the prefix is taken, this would be like this. I could sort the rest of the array. This would take a second operation, right? And as we already took this operation, this would be our third operation. This is actually our first one, but yeah. So this marks 1, 2, and 3 equal to 3 operations, right? So this is basically an edge case that we need to handle. And this only occurs if the least element is at the last and the largest element is at first and there is only one occurrence of it, right? Otherwise, there could be, what if this was like this, H, F, C, H, B, A, right? Then we have two, as we have two largest element, we could take this suffix and sort, right? This would become A, B, H, H, F, C, and then we could sort this suffix, right? So this would work. But if we have only one occurrence and this to here, this is going to cause some problem, right? So this is the problem with it. So yeah, after noticing that, we could actually perform a write our solution, which would be basis on this, right? First, we place the smallest element of the largest at its position, and then we sort the rest array. Also, we need to also check if it's already sorted or not. So let's go through my solution for once. Yeah, this was my solution. So yeah. So here, this is our answer array, right? Why I'm using this to check if it's already sorted or not. This I'm checking if it's already sorted. If it's already sorted, return 0, right? And if this checks, if the first element is the smallest element, this check if the last element is the largest, we would just require one operation, right? We have already satisfied this. We need one operation to sort the rest of the array, right? So this basically does this. Here, if n is equal to 2, this is the edge case. If n is equal to 2, that means this is xg or something. We cannot do any operation here because there are only two elements, right? So no operations. So we are going to return -1. Got it. Here I'm just checking the first and last position of smallest and the largest element. Why I'm checking this? For example, this itself. For A, the position is 336. If we are taking zero base index, and this is 5. And for H, we have 0 and 3. So I basically check the first position of this and last position of this. If the last position of this is at index 0, and if the first position is at index n minus 1, that means if this two satisfy, that means the answer would be 3. Otherwise, we could just sort the using some suffix or some prefix, right? I hope this part is clear. This is actually very important part. Let's say we took this. Now for A, the first position is 1 and the second position is 4. This is zero based indexing. Now for H, the first position is 0 and the second position is 1. I'm basically here, what I'm doing is this A and B, I'm storing the last position for the maximum element, which is uh this is 2, right? 2, and the minimum position for the first element, which is 1, right? Because this tells us if this is not, this minimum position is not equal to n minus 1, that means that there exists one more occurrence which I could take, right? And similarly this too, if there exists one more occurrence, right? Otherwise, if the smallest is at last and the largest is at first, we are going to return 3. So this basically does this. We are going to check if b is equal to that means the position of the largest element is at first, the position of first element is at last, and there is no occurrence. That means we are going to return 3. Otherwise, the answer would be 2, right? So this is the entire algorithm for the problem. Hope you guys liked it. Let me actually read comments now. What if large is at first and small is at last? Yeah, exactly, right? That would create a problem. So we would solve it like how we did it here. I'll solve all in the 1800. Good, dude. Great. Good for you. You can still watch and see like if I did something new or if you had some new insights, you can actually ping it out in the comments. Right. Let's move towards our final problem. Minimum cost to minimum cost. What was the problem? Minimum cost to partition to a binary string. Why isn't it updating? I hope I'm audible, right? Chat, if I'm audible, do ping out. Let me also see using my device. Am I audible, chat? I hope I'm audible now. Hello, hello, hello. I hope I'm audible. Yeah, so I'm audible. Let's move towards the final question. Minimum cost to partition the binary string. Great. You're given a binary string s and two integer in cost and flat cost. For each index I, if si is equal to 1, this indicates that ith element is sensitive. And if si is equal to 0, this indicates the ith element is not sensitive. Got it. So this is our final problem. and we are going to conquer it. So yeah, we are given two integers, ink cost, and the second one is flat cost, right? And we are given definition of sensitive. We are given a string, and if si is equal to character 1, that means that this element is sensitive, otherwise it's not. The string must be partitioned into segments. Initially, entire string is a form of segment, a single segment. For a segment of length L containing X sensitive elements, if X is equal to 0, the cost is flat cost. If X is greater than 0, the cost is L, the length into X into N cost. Got it. If so basically we are given some criteria to calculate cost of segment. If X is equal to 0, the cost of segment is flat cost. Otherwise, it's going to be X, the number of X is basically number of sensitive elements in the string or substring. Or in the string, we are calculating the cost. X into L into ink cost, this one. Got it. So basically, we need to check with this is how we calculate the cost. Got it. And we are told we need to divide it into some segments. And what is the criteria for segments? If a segment has even length, you must split it into two contiguous segments of equal length. And the cost of split is the sum of cost of resulting segments. Return an integer denoting the minimum possible total cost. Got it? What we need? We need minimum cost. Minimum cost. Right, this is we need to find, and we are told, let's say we have some array, we could basically partition it into two segments. Let's say its length is L. If it's even, we can partition it into two elements, each of length L by 2. And the cost of this L length segment would be equal to cost of L2. Let this be L2 and let this be L3 plus L3. So this is our entire question. We are given two integers. One is in cost and flat cost. Another thing we are given is a string s, which tells us if ith element is has the value as character 1, that means it's sensitive. And third, we are given to calculate, given a formula to calculate the cost. If first we'll calculate x, which is number of sensitive elements, right? This x. If x is equal to 0, that means the cost of that segment is going to be flat cost. If it's not 0, if x is greater than 0, the cost of that segment would be x into length into in cost or whatever. It is in cost, right? Yeah. And we need to find the minimum cost. This is what we need to find. And we are given we can actually partition a length into several segments. How are we going to do it? We are going to basically, when we partition, we first need to make sure it has even length. Then we partition it into two even lengths segment. And basically the cost of this entire segment would be now this plus this segment if we partition it. Otherwise, this would be cost of this segment using whatever formula we have. Okay, great, great. Let's actually understand it using some problem, some example basically. So this is our example. Let's say this is our string and our INC cost is, that would be 2 C's by the way, 2 and flat cost is equal to 1. Our flat cost is equal to 1. Great. So what we could do is, basically what we need to do is, find the minimum value we could get from this segment, right? What was the value of this segment itself? Here x is equal to the number of sensitive elements, which are 2 here. Length is 4. What would be its cost? Let's make it L1. The cost for L1 is equal to x into L into the ink cost, right? For this problem, let's denote this ink cost by E and this flat cost by F for our convenience. Right. So what would be this? This would be 2 into 4 into 2. 4 to 8 into 2, 16. So this is our final cost of L1. Now, can we actually divide it into segments? Right? Yes, we can. We can actually divide it because its length is equal to 4, which is even. So let's say we divided it. So this would be 1, 0 and this would be 1, 0. What's cost of 1, 0? Here x is equal to 1. Length is equal to 2. So the cost, let's assume this is L2 and this is L3. As they both are same strings, the value of this would also imply for the value of this. So its cost would be equal to L2 or L3, as they both are same, x into L into the ink cost, which is E. So this would be 1 into 2 into 2, which is equal to 4. Right. So the value for this would be 4 and the value for this would be 4. So if we divide it here, our answer would be 4 plus 4. This would be equal to 8. And this is much better than 16, right? That means that dividing once, only once, give us a very better answer. Let's actually not stop here, divide it much even further, because 1, 0, the length is equal to 2, which is again even, right? If we divide it, we get 1 here and we get 0 here, right? And what's the value for this? We also have the right side, right? Here we also have 1 and 0. So this would be 1 and this would be 0. Let's calculate for this. The cost for this, eh, as x is here equal to 1, would be x into L into ink cost. So this would be 1 into ink cost is going to be 2. So this gives us 2. And for 0, its cost, let's assume cost is written with C. This, as x is equal to 0, this would be equal to flat cost. F or flat cost, this is equal to, F is equal to 1, right? Here we have it. Yeah. So this is basically what we have. So this is would be equal to 1, this would be equal to 2. For that means that this, the cost of 2, 1 would be 2, this would be 1, this would be again 2, this would be 1. So total would be 2 plus 1 plus 2 plus 1, which is equal to 6, which is even better, right? We got 16 in our top segment. Later we got 8 and then we got 6. This is the best possible answer, right? So this would be our answer. We are going to return 6. Now this is how we did the first problem. The very first brute approach would be checking for all possible segments, right? Also, one more thing, don't assume that for this the answer is always better when you keep dividing the segments. You never know. Right. For this, the answer is 6. Yeah, we keep divided into segments and our answer reduced by a lot. Let's say for this example. For example, we had this. Only 1 0 and the flat cost is equal to 10 and in cost is equal to 1. What's its entire cost? This would be 1 into x is equal to 1, right? Into L. L is equal to 2. Into increased cost, which is equal to 1. 2. But let's say we divided it. Right, this is even, we can divide it. We divide it into 1 and 0. What would be its cost? This cost would be again 1 into 1 into 1. X is equal to 1, length is 1, and ink cost is equal to 1. This is 1. But for 0, the cost would be equal to flat cost, which is equal to 10. So the C would be equal to 10. And 1 plus 10 is equal to 11. But initially here, our answer was 2. But this is 11. This is much greater. Right. This tells us that always dividing doesn't mean that it would always decrease our sum. It actually depends on these elements. Right. This tells us that greedy wouldn't work. Or like greedily or basically always dividing doesn't work. This is an observation. Right, that always dividing doesn't work. So what else we could do here? Right. So this was our first observation. So how are we going to solve it? If we cannot solve it by always dividing, that would mean that we need to check for each segment, right? So very brute force approach would be to basically check for each possible set of segments. But right, but there is one more thing that we need to notice. Let's say we did something like this. We could actually divide it into 1, 2. And what if this we still need to divide? Still divide. If we actually go through the if you run this down through dry run this down, the best possible if the flat is equal to 1 and n cost is equal to 2, we could actually divide it here, and this 1010 you can actually see our first element was this, and it resulted in 6. Right. So this for this segment, the best possible answer is 6. Can we say it? Right. Because this segment we already calculated it here in the first example. And for this, the flat cost is equal to 1. So this would be equal to 7. This meant that for this segment, we need to basically completely divide it. And for this segment, we need to keep it as it is. That means we never know which segment needs to needs to be divide by how much, right? We cannot make sure. So that means that the greedy wouldn't work. And whenever the greedy doesn't work, what works? Either recursion or DP, right? So what I thought, what we could do is here. How about we store all the possible values for the segment, right? There could be at max 20 depths for the segment because n here, let's actually see the constraint, is equal to 10 raised to power 5. Let's place the constraints here, that n is less than equal to 10 raised to power 5 or 1e5. Right, am I right? Yeah. That means that if we keep on dividing, these blocks, we could at max go roughly around 20 times, right? We would at max go 20 times deep. Can I say this? Because each time let's say if we had this length n, right, we divided it, we turned into n by 2 into n by 2. Later we will go n by 4. Right. And similarly we will go down, and for at last we will reach 1 1 1 1 or some odd integer for this length, right? So this, the maximum depth would be log 2 of n max, right? And this would be around 20ish. This would be less than 20 actually. I think this would be around 16 17 or around it, right? Right, we could say, let's say for safe case this would be around 20. So what we could do, we cannot apply greedy here. We need to check all possible outcomes, right? What if I stored for each segment, how was it, uh, for each segment the value for it, right? This means that for this segment, I would store value for these, right? And then I'll store value for these, and then I will store value for this, and then I'll use a DP, and which DPI tells us best or minimum cost to cover first I elements. First I elements, or actually cover elements till ith index. Are you getting it, chat? What I thought was basically take this array. This is our array, our string, sorry, 1010 and 4 times 0, right? We'll break it as much as we can, and we will store all the segments that we got the value for it. We'll store the value for this segment. We will once get this segment, right? We'll also get this segment. We'll store value for this. We'll also get value for this segment. We'll also get value for this entire segment, right? And using these values, using dynamic programming here, I could check basically. We will use dynamic programming and DP, where DPI tells us the minimum cost to cover all elements in the ith index, and we could check basically what is our perfect answer, right? For this index 1010 and 4 times 0, when we break it down, we will store for each segment we got it while breaking it down. We'll break it down like this, and we'll at max, like we will break it down as much as we can, and we'll get the answer for all the segments, right? We'll get answer for this segment, we'll get answer for this segment. And this DP, what this is going to do is basically going to check for all these available segments what is the best possible way, so that the minimum cost to cover till the ith element is as minimum as possible. So the cost to cover till ith element is as minimum as possible, right? Period. So first we broke down this to all the segments. We get the answer for all the segments, and basically what we could do is we could use a DP state for ith index. Like for, let's say we are consuming this segment, so this would be around, this would be like the segment sum, segment cost plus DP I minus segment size, right? And as we need the minimum possible segment, we'll add a minimum here, minimum of this comma DPI. And for all possible segment, for this segment, then this segment, then this segment, we'll try all possible cases, try all possible segments, right? For this example, let's say first we broke it out. So this was 1010 and this 0. The value for 1, we will first break it out as this segments. The value for 1 is going to be, I think it's going to be 2, right? And for this is going to be 1, 2 and 1. How did we calculate it? We have already calculated it here in our first example we did, right? We actually basically broke it out, right? So we are using it to save us time, right? And we calculated for 1, as x is equal to 1, length is equal to 1, and in cost is equal to 2, the answer would be equal to 2. And similarly for 0, the answer would be equal to the flat cost, which is equal to 1, right? Similarly for this is going to be 1, 1, 1 and 1, right? Because this is the flat cost. If there are no ones, the flat cost is 1. For this segment also, this is going to be 1, this is also going to be 1, and for this too, this is going to be 1, right? And similarly for this and this, I think it was 4, as I remember. Let's actually see what was said. Yeah, for this it was 4 because x is equal to 1, length is 2, and ink cost is 2. Great. So this is 4, this is 4, and this is equal to 6. Right. So for each segment, we are going to use this DP. For each segment, for let's say we are here for this segment and this there is only one segment available here, right? This one. We are going to check the end points of it. If segment ends here, that means we can use it at endpoints. End point of segments. Right. That means that DPI would be equal to segment cost, the cost of this segment, plus the cost of the best possible answer we could get before this segment, and we are basically going to take minimum for all the segments, right? So using this formula, using this breaking power, we are going to calculate our answer. Hope this is crystal clear. If you still have doubts, you can actually ping it out in the comments. And basically, I'm going to check the comments even uh, after the PCD. So basically, you can actually ping it out later too. It wouldn't matter. Okay. So let's move forward. How are we going to implement it? This we can actually do it pretty brute force. Let me actually show you my solution too. These all 4 solutions would be given to you in the comment section. Well written, using best of the comments we could have and best of the solution I could put it out. Right, because this solution currently is my solution that I wrote between the contest. Right. So using dynamic programming, we did it. How? First, let me actually tell you about my solution, how we solved it. This is basically calculating is the prefix. Why are we calculating the prefix? This is the calculating the prefix for x. We broke the problem into 2 parts. First, break and calculate for each segment. Second, use DP to solve for each segment. For each segment. This is our algo, right? So this is how we did. This is basically here in this loop, I'm just breaking it down until we break when this V break occurs, when the segment size that we are going to is not even, right? So let's see step by step. First, let's here I'm just initializing the size of the string. Let's take this DP is basically my bad actually this DP is basically storing the segment, basically these segments, right? The segments that we need to store, and our answer is here what we have written DP in my solution, it's answer, right? And this DP is I'm using, basically this DP is just a variable name, right? I'm just using here to store the segment answer here, right? So what I'm doing here, while true, there is initially only one segment, this pair here I'm pushing all the segments. Which segment we have is from 0 to last, right? This tells us what segments do we have currently, right? So we start, this is basically I'm iterating to all the available segments currently we have. For each segment, this LNR tells us the current segment. This X, for each segment we need to calculate the value of X, right? To calculate it efficiently, we could either loop, or either you could use prefix sum. So I'm using prefix sum, right? For example, this is our string, and we need to calculate the x for it. We need to the x is equal to 2. We can either loop it, or we could actually store. Let's say we need to find x for this segment. This is equal to 1. If we loop it, this is going to take us nth time, right? This is too expensive. If you use prefix sum, this is going to take off 1, because we are basically just storing it in the prefix sum array. The prefix sum array for this would be equal to 1 1 2 2. So the prefix sum, this can easily be calculated using this formula, which is right minus left minus 1. So this I'm calculating x, then I'm calculating the cost. If x is greater than 0, then it would be in cost into length minus x. Otherwise, this is going to be flat cost. And here I'm storing it. What is this? This storage does? This stores R, the rightmost index. This we could say DP, depth actually, DEP, DEPTH. For broking, we are basically also storing the segment's depth. This tells us depth is basically or depth or size of segment. Instead of storing actual size, there is one observation that the sizes would always be in this format, 2 to the power y. Y could be any variable, right? This y I am storing here, y, right? Using this y, we could calculate the size of segment for each segment, right? This is basically going to what we are going to do, and this is what we are going to iterate for when we are actually calculating for each answer, right? So this is what I'm storing, and then basically if this current segment is divisible by 2, we can actually process further, right? So this is how I'm processing, and then we basically break if it's odd, right? And this is just calculations to make sure if v break is 0, that means we break. And this is just telling us what segment, as we are just pushing in the pairs into the vector of pair, right? This just tells them how what range to basically iterate on. If you are reading it, when you will get the solution, that would be pretty well and well commented, so it wouldn't matter. And this is basically our answer. So for calculating our answer, this we are calculating for each segment possible. This is our formula. This previous tells us the previous answer plus the current segment what we are having, right? So we basically for DPI is equal to this formula we had, segment cost plus what is the segment cost, let's say for this would be equal to store, let's say we are at ith index, so would be equal to I, and we are checking for jth segment, then this would be equal to j. J is basically tells us about the size of the segment, right? This minimum, because we need the minimum answer, plus the previous would be equal to dp I minus 2 to the power j, because this is our segment size, right? Comma dpi. We have to take minimum the answer, right? So using this formula, this basically checks us, this basically help us to check all possible ways for the segments, right? For any segment, let's say again, just one more example. Let's say for this, we have this segments, right? Let's say we are at this index. We check for all these three indexes, right? And the DP for 3, 0, 1, 2, 3, right? 3 would be either equal to minimum of all these three segments. So we would have store I is equal to 3, j is equal to initially 0 plus dp I minus 2 to the power 0, 3 minus 2 to the power 0 is equal to 1. So this is basically this dp2 is dp2. dp2 is this one. So we check for this segment plus this perfect answer for this. Similarly, this segment plus perfect answer for this segment. So this is how we store for check for all possible segments. Hope the problem is clear. And this is how we have implemented it here. This size is basically how we are calculating. This is 2 to the power j, or we are just left shifting it. It's the same thing. This previous tells us the previous best answer, right? And this is basically our final answer. I'm going to provide the best possible commented and well explained code for each of the solution for each of the solution would be in the comments itself, so you can actually just check it out, right? So I hope all the answers were clear. If you liked it, if you loved our efforts, you can actually like and subscribe it. If you have any doubts, if you think you have better approach, or if you think that you need to discuss something with me, you can actually ping it out in the comments, because I will be actively watching comments. By TLE. So yeah, my review would for the round would be, it was actually pretty easy. All the problems are pretty easy, I think. The first problem was actually easy. The second was also easy. We just need to make sure we don't do any integer overflow. The third problem, the minimum operation one, was actually an observational problem that we need to notice that we could actually do it in 0, 1, 2, and 3 moves. The fourth problem was actually more of an implementation problem. How are we going to implement it? I got a lot of WAs because of it. Also, I was like little sleepy, so yeah, it was a purely implement. I think observation plus intuition plus implementation, but yeah, good implementation problem. So yeah, this was all for this for today. If you guys liked it, you can actually ping it out in the comments and like and subscribe and share with your friends actually. So yeah, see ya. How also like, let me read few comments. I saw ad coder 448 beginner. No, this is lead code problem. Lead code solution, dude. Not ad coders. How many of you are knight in lead code? I'm not a knight, but yeah, it's great to be knight, but don't actually, doesn't matter the tags, right? To problem solving. If you have any more questions, you can actually ping it out in the comments. I'll wait for 1 or 1.5 minutes, or either we could end it. Should we end it? I hope my chat is also updated. Yeah, it's up to date. Yeah. Yeah, so let's end the stream now.